In this video, I want to say a few quick things about the index of refraction that we talked about in class. So briefly, what we know is that the speed of light is really close to 3 times 10 to the 8th meters per second. Here's the actual value, at least to several digits up above. So the speed of light is given by the constant c in physics. We're just going to take it to be 3 times 10 to the 8th meters per second. But now here's what happens. When light enters different types of media that are not a vacuum, it slows down. So let me just mention a couple things here. We can determine what the new velocity will be by taking the velocity of light, c, and dividing it by n, something called the index of refraction of the material. So let's just quickly talk about this in terms of air. So air is very close to a vacuum. So the index of refraction here is 1.0003. So you can imagine taking the speed of light and dividing it by that number. You're basically going to get still 3 times 10 to the 8th meters per second. So we don't really mess with it when we're calculating in Physics 202. But just so you know, air actually does slow down light a little bit. Now water is a little bit more. Index of refraction is 1.33, so we'd have to take the speed of light and divide it by 1.33 to find its velocity in water. Now when you get to other substances, glasses, different types of glass, anywhere from 1.4 to almost 1.6, diamond, all the way to 2.42. So this will really cut down the speed of light by a substantial amount. So for example, if I wanted to calculate the speed of light in water, I divide by the index of refraction, I get 2.26 times 10 to the third. And glass, typical glass, divided by 1.5, that's going to give 2 times 10 to the 8th. So that's a third of a loss of the speed of light when it goes through glass. Now, a couple other things I want to mention about it is not only when it goes to a different substance does it slow down, but there's certain things that change and other things that don't. So the speed is reduced, that's what we've just been talking about, but the frequency will stay the same. So the frequency of light is not going to change. Well, what does that imply? Well, since we know that frequency times wavelength equals the speed for light, so these are inversely related, as if the frequency goes up, the wavelength must go down if you're going to keep the constant speed. But now what we're talking about is what happens if we change the speed. If we change the speed of light and we know that the frequency is constant, then that must mean the wavelength is reduced whenever light enters a medium that slows it down, something with an index of refraction greater than 1. So the wavelength must be reduced also. So if I look here, here's a simple diagram. Imagine I'm traveling, I've got a wave of light here, like this. I'm traveling this way, and I go from a vacuum into some material that has a high index of refraction. So I'm going to exaggerate it here, but what it looks like is this. Here's the wave going back and forth, and now it enters this new medium, and it looks like the wavelength is shorter. Well, it is. Okay, so the wavelength is shrunk. The speed of light is shrunk, so now some v, but what isn't changed is the frequency. So these are the things to remember. An index of refraction is just a number that you divide the speed of light by in order to get the new speed of light in that medium. And the speed of light is approximately 3 times 10 to the 8th, and almost everything else will slow it down. And when it slows it down, what it does is it reduces the speed, that's what slowing it down means, but the frequency stays the same, so the wavelength must be reduced. That's what happens. And this has important consequences when light doesn't travel straight through an interface, but when it travels through at an angle, and that's going to cause it to bend, as I'll talk about in the next video.